Last week we introduced you to static electricity, which was about charges sitting somewhere and waiting to go do something. And then pretty soon we're going to be talking about electrical flow, electrical dynamics. But for right now we're going to take a little moment in between those and talk about how do we know if a charge is existing somewhere? What can we do with a charge that is sitting somewhere? Can we detect it? Can we transfer it? Can we store it? And we're going to look mostly at historical methods of doing this. Your book spends a lot of time on the history of electricity in this chapter. And that's good, but I'm not going to test you necessarily on names and dates, but knowing the development of the technology is important. So detecting and storing and transferring charge is the topic of the day. So first of all, detecting charge. An electroscope is the name of any instrument that you use to tell if there is a charge there. There are some very simple versions of this. There are some homemade versions of these, and in your menu assignment for the week, there's that video that shows you how to make an electroscope. If you just watch it and take some notes, then it's worth 10 points. If you actually follow his instructions and make an electroscope and bring it in so I can see it, then you get all of your menu assignments. You can get another 30 and you'll be done with your menu for making an electroscope. So it can be simple, it can be homemade, or modern ones that are made today for electricians and for industry are quite complicated, and digital displays and things of that nature. But the idea is that you have to measure an electric field and see if there is the presence of an abundance of electrons there. And most of the time when you measure an electric field, you diminish it because you are taking some energy away from that field to make your electroscope do something. So an electroscope is kind of a historical tool. It says, hey, there once was a charge of this much over there. But when you measure the field, you absorb some of the energy. You take some of the energy from the field to measure it. So it's hard to measure an electric field, the presence of a charge, and leave it alone. Even simple things like when we rubbed the balloon on your hair and then brought it near somebody's head and the hair stood up, that's an electroscope. You were seeing, yes, there's a charge there. But if you had kept doing that over the course of time, that would start to weaken the field, and less and less hair would come up and respond to the field. So measuring a field diminishes the field. Electroscopes are therefore historical instruments. They say what there once was. This is a picture of a very simple historical electroscope. And if you make one for your menu, it will look something like this. This is the basic design. An insulating jar, like a glass jar, and then a rubber stopper and a conducting rod that goes down through the rubber stopper. So the rubber stopper is insulated against the jar, and the rod is insulated against the jar, and it's all contained in an insulating material here. And then two thin foil leaves attached to the rod. Tin foil is the easiest thing to use. And then if you bring a charge near the top of your electroscope, what happens is, in this example, you're bringing a region of positive charge near the electroscope. The region of positive charge will attract electrons from the foil and the conducting rod up near the top, because the electrons would like to come up here. Well, that leaves a region of positive charge on the foil leaves, and because they're both positive, they will repel each other, and the tin foil will stand out. And so it would work the same way with a negative charge. If you brought a source of negative charge, all the electrons would run down to the foil leaves, and then the foil leaves being of the same charge would stand out. So the electroscope doesn't tell you if it's a positive charge or a negative charge that you've encountered. It just tells you that you've encountered a charge. But by doing that, you're going to lose some of this field strength, and if you kept testing the same charge over and over and over again, eventually you won't get it. Okay? So electroscopes, this is one of the earliest examples of them, and if you make one, it's going to look something like that. This is another one. This is made in the modern day, but it's the same design. Glass Erlenmeyer flask, rubber stopper, metal ball, metal rod, and 2 pieces of aluminum foil. And so that's the same idea. It's going to, these foil leaves are going to spread if there's a charge brought near the metal ball. There are also electroscopes that are made like this, where this gauge needle would like to be straight up and down because of gravity. This is a little bit heavier than this side, and so it likes to sit straight up and down. But if you bring a charge near it, then the charge is carried down the pole, and the needle and the pole will wind up repelling each other, and so the repulsion tips the needle away from the pole, and you get a reading. So that's another example of an electroscope. And again, it doesn't know if it's got a positive charge or a negative charge, it just knows it's charged. And so you can see the presence of a charge there. And this woman is an electroscope. And some of you will look like this on Friday. And so this woman has had charge added to her. And so the electrons on the hair repel each other. Now, there are electrons all over her body, but her neck can't repel her shoulder because it's, the neck is too strong. But when the electrons get spread out throughout her whole body, the electrons on the hair can stand up and repel each other because the hair is light enough to respond to the electrostatic force. So the more charge that this woman absorbs, the more of her hair stands out. And our goal on Friday is to get some of you young ladies with like huge cotton ball puffs of hair going on.
Let's do it.
And so that's going to be what we try to do. And so this is a human electroscope. Okay, transferring charges. So we can detect if there is a charge. Well, rather we can detect if there was a charge, and there's still one there, but it's gotten weaker. Transferring. What do we do with that now? Now that I know there's a charge, what can I do with it? Well, I can move it from one place to another. If electric charge is moved from one object to another object, we call that a discharge because the charge has left the thing that it used to be on. It was charged, now it's discharged. The charge has gone somewhere. When an area of high electron density comes in contact with an area of low electron density. So kind of like heat, it's you bring a hot object and a cold object together, and the thermal energy moves from the hot object to the cold object. What thermal energy resides in the cold object does not move up to the higher thermal energy object. Same kind of thing with electrons here. Electron density always moves from higher regions of electron density to lower regions of electron density. Nothing ever goes from low density to high density. Natural. You could have a machine get that done, but naturally that's not going to happen. So the electric discharge always goes from a region of high electron density, which would be an area of negative charge, to an area of low electron density, which would be an area of positive charge. Electrons are what move. Protons don't move. And we can do that by direct contact or by jumping through the air. So if you charge an object, you could even charge yourself. If you put on socks and scooted around the carpet, you would charge yourself with electricity, and then you walk over and touch a metal doorknob or touch a friend, and the electrons will jump through your contact into that other object. And so that's a direct contact discharge. Or you could charge yourself and come very close to somebody else and watch the electricity jump from you into the other person. One of the more amusing things that I did once when I was a younger person is I had a friend who had braces. So they had metal on their teeth, right? And it's all wet, so whatever electrical stuff happens in the braces goes into their gums. And I was raised in Southern California where it's a lot drier, and you can quickly build up a charge by scooting around in socks. So I built up a large charge. I scooted around for like a minute in my socks, got a huge charge. And I walked up to the person, I said, "Smile." I smiled, and I went, and I touched their braces, and it shocked their mouth. And they were like, "What did you do to me?" So
So
that was a direct contact because I touched the braces. But if I had held it a little bit farther away, I could have watched electricity jump through the air. That's called an arc. So, but electricity can discharge through direct contact or by jumping through the air. So direct contact, we're familiar with wires, right? Electricity goes from an area of high electron density to an area of low electron density. The electrons move through the wire, and this is all direct contact. The battery is in contact with the wire, which is in contact with the electrode, which is in contact with the filament, contact with the electrode, contact with the wire, and back to the battery. Nothing is sparking here. So this is direct contact. This is an arc, where you have one conductor and another conductor, and there's a little bit of a gap between them, but the gap is small enough that the electricity is able to jump across the gap. So these are electrons taking a flying leap across the wire gap. And some sparks are really small, some are really, really big. And I will show you some examples of large discharges here.
Wait, it's like those old light bulbs where they have like two metal pieces.
The little wire goes between them. There's a little wire, the silicone. Yeah. These bulbs, the fluorescence, it arcs through the air. There's no filament. It arcs through the air there.
Mr. Ali, was that a true story? You really did that?
Yes. I shocked a friend in the face. Yes.
How come, like, when you know how at Costco they have the metal things, right?
Yes.
How come, like, when you touch it, sometimes it just, like, randomly shocks you?
Well, because you have built up static charge somewhere in your clothing rubbing around. So those are grounded.
If you're using, like, a metal watch and then you touch that, would you get shocked?
The metal watch probably has nothing to do with it. Okay.
But like, what if we don't have carpet? Because I've like experienced the shocking before while like opening a door, but we don't have carpet.
If you're wearing sweatshirts or any kind of fabric that can build up a charge too. Okay. Substances that allow electrons to flow easily are called conductors. Substances that do not are called insulators. So same terminology that we used with heat a couple of chapters ago. Thermal energy flows through conductors. Thermal energy does not flow through insulators. Same exact terminology here, okay? So things that are good heat conductors are also good electrical conductors because both of them have to do with free electrons and free particles that can move around. And if something holds its electrons loosely, then the flow of thermal energy can use those loose electrons to travel well. And it'll also use those free electrons to conduct electricity. Substances that hold their electrons very tightly, neither thermal energy nor electricity can use that material to flow very well. And of course, it's a sliding scale. It's not like everything in the world either belongs in one bucket or another. Some things are relatively good conductors, and then other things are marginally good insulators, and then there's good insulators, and then there's awesome insulators. And so there is a scale. There are some things that are in between. But generally speaking, we call things either a conductor or an insulator if it will allow electricity to flow through it, and we can complete a circuit with it or something like that. Okay? Very few substances allow electrons to flow in specific circumstances, and those are called semiconductors. That's what computers are based on. So silicon is an insulator, unless you do certain things to it, and then it does allow electricity to flow. So in a silicon microchip, most things are like gates. They don't let the electrons flow, but then the computer can manipulate the condition of that silicon, and now it'll allow it to flow. And so certain materials like that can flow or not, depending on their circumstances, and we use those in a lot of circuitry, semiconductors. And then there are things called superconductors that conduct incredibly well, so that there's almost no resistance. So most materials, though, fall into the bucket of either a conductor or an insulator. Here's some examples of conductors, right? These wires, they're all different kinds of metal. Metal is a good conductor. Only a few metals are poor conductors. Most metals are good conductors. So all these wires made out of metal, and electricity flows down it. But plastic is a pretty darn good insulator. So on high voltage power lines, they will attach the power cable to the the structure with these big plastic, hard plastic devices that insulate the electricity from the wood. Otherwise, if the wood were exposed to all this electricity, the electricity would get the wood to catch on fire and you'd have all kinds of problems. So the electricity travels through this little loop of bypass wire, and the tension is maintained on the wood board. And so this plastic helps insulate. Okay? And then semiconductors, again, computer chips are made out of semiconductors, and the silicon that this is made out of most of the time does not conduct, but by manipulating certain aspects of the structure, it's made to conduct, so it's a switch. And the last one, storing charge. So we've detected charge, we've transferred charge, now we're storing charge. Storing electrons in a great concentration for later use was a challenge early on. There's some humorous things about the invention and the discovery of electricity. When Benjamin Franklin did his famous experiment with the kite and the key, and he was able to turn electricity, people were able to do things with electricity at the moment of electrical generation, but how do you store electrical power has been a challenge, or was a challenge, for a long time. And there are certain records of newspaper editors and things like that talking about Benjamin Franklin's experiments, and even Thomas Edison's experiments, and saying, yeah, you know, it's a parlor trick, it's a magic show, it's something that's fun to amuse your friends, but there's really no good use for electricity. You know, electricity is never going to be used for anything. And if those people were able to look 200 years into the future for all the things we've done with electricity now, they would see how wrong they were. But the principal problem was, how do you store electrical charge? Because you can make it and you can do something with it right there. But if you're not going to always be right next to a source of electrical energy, how do you carry that around? The key was to provide an insulated place for electrons to be stored. So electricity is the movement of electrons. Electrical generation makes a pile of electrons, but then where do you put that pile of electrons, and how do you get them to sit there for a long time? The first method was developed in a city named Leyden in Holland, and so it's called a Leyden Jar because of the location of its invention, and that was in 1745. Hold on, let me see. 1745 in Holland, there you go. The Leyden Jar, named after where it was invented. And this is a Leyden jar. It is a glass jar, and the inside and the outside are both coated in lead initially. You can use any metal, but lead was the initial metal that was used. Okay, and then you insulate a metal rod going through the glass jar with a rubber stopper, so the metal rod can't contact the glass jar. And then you put a chain at the end of the metal rod. So you have a conductor that goes down to the inner lining of the metal jar. And then you have an insulating surface. And then you have another surface. And this one obviously is grounded, because wherever you set the jar, this gets grounded. You can make Leyden jars fairly simply. And I have one here that we have made in past years. And it sits kind of calcified on top, so we break this off. But a Leyden jar is pretty simple to make.
What is that?
It's corrosion that has developed on the wire, copper corrosion. But this is a student's-made Leyden jar. Okay, electrical foil. Aluminum foil on the outside, and a glass jar, and a conducting surface, conducting liquid on the inside, and then the wire is insulated by the cap. The cap is conductive, but the silicon is not, and then the cap can't contact the foil. So this is a homemade Leyden jar, and you will be making some things like that on Thursday and Friday. And the general idea here is you build up a charge here, and the electrons can like hang out in here, and then they can't leave unless you bridge the contact from the metal rod to the outer case. So Leyden jars can be used one at a time, or this is an array of Leyden jars, where all the Leyden jars metal rods are connected in series, and so and all of their plates sit on a common lead plate down here, and so each one of these can store charge, and then when you put 6 of them together, they can store a lot of charge, and so this is a early attempt at a battery. Okay, modern versions of this are called capacitors. A capacitor is much smaller than a Leyden jar, but it's the same idea. It's a place where you can put charge and have that charge build up, and then you can discharge that whenever you need it. Capacitors are, like I said, it's an early concept of a battery, but they tend to give all of their electricity at one time. A capacitor doesn't slowly bleed out its electricity. So if you need to store electricity, you can, and then once you go to use it, if you want all of it at one time, the capacitor is your friend. If you want to use it out over a long period of time, then capacitors aren't great at that. But most electronic devices have a capacitor of some kind in them, and they use them to short-term store a little bit of electricity. The amount of electrical charge that can be stored is called the capacitance. So that's the value of it. A capacitor will be rated with a certain amount of capacitance. How much electricity can this device store? And then we will measure capacitance in a unit called a farad. So a farad is going to be the unit of measure, like the metric unit for stored electricity. So if you ever get into electronics and you are looking at capacitors, capacitors will come labeled. You know, this stores 3/1000th of a farad. A farad is actually a large amount of electricity. Or this stores a half a farad. If it does store 1 farad, that's a big capacitor. If it stores 10 farads, it's a monster capacitor. Okay, so farads are a large unit of electricity, and the more charge it can hold, the more farads it's rated to. And I've got some pictures here of capacitors. A capacitor, same concept as a Leyden jar. You have 2 conductive surfaces separated by an insulator. The word dielectric is just another word for an insulator. So 2 conductors separated by an insulator. You could have a capacitor that is a big long sheet, or you could take a big long sheet and roll it up into like a I don't know, like a slinky sort of design. And this rolled up layer has 2 conductive surfaces separated by 2 insulators. And what that winds up doing is you have the very large area here of this big capacitor all rolled up into a small area, and you can have a lot of capacitance in a small region. Okay, so then when it's all done, it looks like this. This is what a capacitor looks like. It's a sheet of insulator separated from another sheet of insulator by, a sheet of conducting separated by another sheet of conductor separated by some insulator. And so one of these electrodes will go to one conductive surface, and one will go to the other, and then it's all wrapped up in paper. That's what a capacitor looks like. Capacitors come in all different sizes. Small itsy-bitsy capacitors to rather large capacitors. They do kind of look like batteries, and they serve like batteries, except they release their energy all at one time. So some of these, like this one, you can see 3,300 microfarads. A microfarad is a 10,000th of a farad. So this is 3,300 10,000ths. Basically, it's about, why am I having trouble with this? It's 0.003 farads. It's a small fraction of a farad. This one is 22 microfarads. This is 220 microfarads. This one is 45,000 microfarads. And so this is again not even 1 farad, this massive capacitor. So a farad is a big large amount of electricity. When you discharge a capacitor, you get a lot of energy all at one time. So this is actually a battery that they were using to charge the capacitor. And then when they bridged the circuit to let it discharge, this huge spark came out. So capacitors tend to give all their juice at one time. And this is awesome. You need to see this. Okay, he's not talking, so let me interpret for him. What you saw a moment ago was a switch, and this is a wire, and then the other end of the wire, they're going to go to this watermelon. And down over here, they have a huge capacitor, an array of capacitors, and they've got a lot of electricity stored. And they're going to let this watermelon bridge the circuit. It's pretty awesome. So, one wire, another wire. So the watermelon will bridge the circuit.
Questo tipo.
They're not speaking English, so it's okay.
Yeah.
Isn't that awesome?
The heck?
Yeah.
What the heck? Oh. Did it whack him? Or
Yeah.
anything?
Vittu mennä täällä haisee mulle.
Oh.
They'll show it and stuff out, because why not?
Well, it looks cooler in some way.
Yeah.
Have you played the watermelon game where you gotta put the rubber bands around it?
Oh, I've seen it.
Yeah.
Yeah. So anyway, that is let's see, how do I-
Yeah, you put as much until it pops. Until it blows up. So like you go around in a circle, and then your steering can go around. And you can see it like sinking in. That's right.
Okay. So there you go. Capacitance and storing